4 and 5. I couldn't get the 1 and 1 thing going.
That looks
Could
good.
be no, it's not bad. Yeah. We're right there, basically. Sort of.
20 grams.
Yeah, that's cool. Might be down or-
2 graphs. And 3 got. You said group 4 you're having a problem.
No, 4 is no good.
So one of these is missing. Is this the one I sent you?
Mm-hmm.
It didn't work.
Mm-mm.
Oh, wait a minute, there it is. Okay. Yeah, you have everything there. What are you missing?
It doesn't, so if you look at lines, so what you asked us to
Not a good
do
example.
is to compare like display Hines and feature display Hunts, but I couldn't get display Hines to compare with these ones. To be there, like, if that makes sense. So when it,
This one by default is display Hines, because you
Okay.
set that equal to 1, right? So this is display Hines, and then everything else is, so you do have that one there.
yeah,
Now, are they very different? So what he might not have done is running interaction.
oh, because those
Who
are
uses this?
springs.
Did you run dummies in interactions?
Mhm.
You did?
Yeah.
Because we're getting more curvature here. These look
Oh, no, on
more-
the first half I did, and then
The second half
we
you
didn't
did?
do it on the second half. no.
Okay, yeah, because that's what it looks like. Those look more like kind of parallel shifts.
First half I
And
missed
we've
that.
got, so yours has more curvature,
Right.
which tells me the slopes, you've accounted for differences in slopes. And his look more like shifts. So you're fine.
Okay.
Different, so,
Okay,
so
but
this
that-
is one of the cases where I said most of the time it's gonna be differences in margins. It's actually differences in the model. Because you should have run the same model for all groups. So you only had to run one probit. The only thing that changes after that is the margins. So one probit,
Sorry.
25 different margins.
Well.
Sorry about that.
So I think you're right.
Okay.
You're probably gonna pass.
Good to know.
He'll be here next semester, you'll be
I'll see you again.
fine. Joke.
Take that easy.
All right, so let's,
Be the only person in class.
again, this is insane stuff. Models of multinomial dependent variables. What the heck does that mean? This is a specific type of multinomial. It's called nominal or unordered. So instead of having a binary, we're going to have multinomial. But the order doesn't matter. So let's assume that we've got 3 outcomes we want to model, A, B, and C. A is no better than B is no better than C, and vice versa. C is no better than A. B or A, these are just 3 different brands of stuff, and we want to model these. So the order in which we model these is irrelevant. We're going to have exactly the same results, depending on how we order, irrespective of how we order them, I should say. Okay, so in essence, what we can do is treat these as kind of 3 binary logits with a common base. So here we can see the probability of choosing B relative to A. And we can see y equals b given an x, which is our independent variables, price and stuff like that, relative to a. And this is a typical binary. And we can model this also as what's the probability of choosing c relative to a. And then we have the probability of c relative to b. But it turns out that we have some redundant information. Following the rules of logarithms, right? The log of a over b is the log of a minus b. So we get a situation in which if we take the log of b over a minus the log of c over a, then we get the log of c over b. So what this is saying is that those first two, if we subtract those first two binary regressions, logits, then we'll get the third one. So we don't actually have to run the third one if we were to treat these as a series of binaries. So we would get the same coefficients by just taking the difference of our b versus a, the first one, and our c versus a, the second one. That would give us the coefficient, our beta 0 for the third one. And taking the slope coefficients, and that would give us the third one, theoretically. Let's see, if we actually ran these, let's see. This data is for occupations. I actually have a better data set. I don't know why I used this as, probably took this from my labor class. Occupations, manual, white collar, professional. So the probability of being in one of these occupations. We can analyze them in these series of binary logits. Let's see, here's our output. And again, we should be able to take this coefficient, subtract it from that one, and get the 0.374. We get 0.376. And instead of 0.433, we get 0.5866. We get close, but not exactly what we're supposed to get. And the reason why we get different results, or the reason why we don't get the results we're supposed to get theoretically, is because in each of our binary logits, we're just looking at these two pairs, so the sample size differs. And essentially what this multinomial process does is look at all these simultaneously using all the data. So we don't use these kind of pairs of binary. So what is this? Okay, so here's the model. It's pretty simple, pretty nasty looking. Yeah, it's real simple. We can kind of almost do this in our head. If you bring your TI-85, you can kind of crank these out in our calculator. Yeah, we got all that stuff. We do that stuff too. Math. And we get something like this using the multinomial logit command. By default, multinomial logit, everything's going to be relative to a base category. And by default, multinomial logit throws out or uses the base category as the category that happens most often. So in this data set, it looks like the manual, labor, occupation is the most common. Then there's, and the white collar professional ones are not as common. Again, these are going to be close to, if we were to run these as binary logits, they would be close to those, but it wouldn't be the exact, again, because we're using all the data with our multinomial logit command. We're using pairs of data sets in our binary logit commands. So again, we can kind of compare these. 0.30 for education versus 0.342 and 0.71 for professional versus 0.718 in our binary logit. So we get somewhat different results, but not drastically different results. Again, because the sample changes. All right, results of stuff mean. Everything's relative to the base outcome. So in this case, the 0.3 under white collar means that, so we have white collar, we have professional, and then we got our coefficient on education. So our coefficient on education means that, again, we still got this log of the odds ratio stuff, but it essentially means that a 1 unit increase in education, a 1 year's increase in education, is associated with the 0.3 increase in the relative log odds of being in a white-collar occupation, relative to the base occupation, which is the manual occupation. So again, there's really no intuitive interpretation of these things. It's changes in the log odds relative to some base category. We're going to have to use margins again, which is the point. We're going to have to use margins again to make this stuff understandable. This is really, really, we saw the math. This is really, really complicated stuff. For professional, you can see, again, the same thing. A 1-year increase in education increases the probability of being in a professional degree by a larger amount. So if you're looking at the relative magnitude of the effects of education, a year's worth of education has a bigger effect of you going into a professional degree than a white-collar degree relative to a manual labor occupation, which kind of makes sense, right? So these are duh. And the results are statistically significant. So we can see our Z statistics. Pretty basic stuff. Marginal effects. Again, we got this nasty stuff, but Stata calculates all these things for us, so we don't have to worry about this. The nice thing about this, the really cool thing about this, is that the marginal effects, again, they're nonlinear. And by marginal effects, we're really talking about slopes, right? Which is, and again, we're still going to get these nonlinear 1, 0. By marginal effects, we're talking about, okay, what's the effect of here, this slope is different than it is here, and there, and then that one's, whoops, that one's relatively flat, just as this one's, whoops, just as that one's relatively flat. So by marginal effects, we're talking about the effects of a 1 unit increase in one of our independent variables, in this case it's education, on the probability of being in any of these occupations. And margins will spit this stuff out for us. We already saw this. So a lot of the same commands that we used in our binary logits are going to be used in these multinomial logits. Except now we just have a whole lot more stuff going on, as we'll see. One thing that is relatively user-friendly is treating these as relative risk ratios or odds ratios. And believe it or not, this actually has some intuitive appeal. So the relative risk ratio just tells you how much more likely you are to be in one category relative to the base category. So here's our standard logit regression. If we add an option in our Stata command, and the option is RRR, triple R, it gives us the relative risk ratios. So we talked about this being a 1 unit increase in education increases the relative log of the odds ratio of being in white collar relative to manual by 0.3, whatever the heck that means. It's a mouthful. The relative risk ratios are actually pretty understandable. And it's actually the same output. So if we take our coefficient here, raise it to e to that, we get the relative risk ratio, which is what we get. Boom. Do I circle it? Yeah, over there. Which actually has a pretty simple, intuitive appeal to it. So basically it says that for every year's worth of education, you're 1.35 times more likely to be in a white-collar occupation than a manual occupation. And that makes sense. Did you break something?
No. Just opened everything I mentioned, I was surprised
Oh.
at the size.
So these actually make sense. So you get these, even though it sounds more complicated, a relative risk ratio, it's really just how much more likely you are to be in one category than the other. And the whole idea of the relative risk ratio a lot of this comes from the insurance field, right? How much more likely you are to be in an accident. So when you're modeling claims, which I guess is befitting for Sonoma County right now, when you're modeling claims, you're literally modeling the relative risk of something. In healthcare, when you're modeling the probability of accidents, this is exactly how you do it. What's the probability that, actuarial tables, this is how they're constructed. What's the probability that the average person breaks a leg? And you've got these independent variables. So what if they're a construction worker? Then you're probably more likely to break a leg. What if they are a football player? Then they're probably more likely to break a leg. What if they're a really old college professor who plays football on Fridays?
Most likely.
Yeah, you're a dead man. I'm just waiting for that day, so I'm still out there every Friday, getting beat up, by the way.
When I interviewed for that supply chain analyst position, they said that they did a lot of risk analysis on suppliers, so they would
Yeah.
measure the risk of certain suppliers.
Probably that they actually deliver on time.
Mhm.
Exactly. So that's what we're talking here. And remember, delivering on time is what? You either do or you don't. It's a binary. It's a 0-1. So that's exactly what they're talking about. That's interesting. That's actually real interesting. And this was Keysight doing this? Because the last I heard, from what I've heard about Keysight, is that they were pretty rudimentary in their analytics. So it's surprising that they're doing something like this in terms of risk analysis. So that's actually pretty good. That's impressive. Yeah, and if we go down to the other one, I guess I only did one of them. But if we go down to professional, again, notice that a year's worth of education has for every year's worth of education, you're 2 times more likely to be in a professional degree than in again, the base category, which is a manual occupation. So again, those actually make sense. You're not talking about logs and odds ratios and changes in the log of the odds ratio. You're more likely to be here, you're more likely to be there. So that's actually something understandable. So kind of having those at hand is nice, although a visual would probably be a lot nicer. Multinomial probit is just the normal error counterpart to multinomial logit. You're going to get nearly identical results, just like we did with multinomial logit and probit. So here's an outcome from our multinomial probit for different categories. Here's our predictive margins from our multinomial probit model, and I did a predictive margins from so this is just using margins, from our multinomial logit model. And you can see that 0.09128, 0.091988, so pretty close. Remember when we did the logit versus the probit, did we do that? They were virtually on top of each other. Did we not do that?
Mm-hmm.
Yeah, we did. So the multinomial probit and the multinomial logit are going to produce nearly identical results. Again, you get thicker tails in the multinomial logit, but it's much more computationally intense for these reasons. They do a Gaussian quadrature versus some other stuff. And we'll do it, by the way, with larger data sets, it's a significant time difference. It's not like a second where it hangs. It'll be, that's actually taking a little bit longer. So I've got a couple of different data sets. The data set that we're going to look at, we're going to look at two of them. One is soft drinks, and the main one is going to be saltines. Who doesn't like crackers? All right. So we got four choices. We got Nabisco, we got Sunshine, we got Keebler, and we've got basically a store brand. So this is, probably Safeway or Rayleigh's or whatever generic store brand there is. We're gonna have these four choices. And we want to be able to model these things. So how do we do this? All right, so let's. Actually, I'm going to switch this to my PowerPoint. It's more interesting than occupations. So we can see what we got. Let's describe the data. This is the household panel data, which means each household is given a scanner where they literally, when they get home from shopping, they scan their own stuff, and we know what prices they paid, and more importantly, we know what they bought and we know what they didn't buy, and we know the prices of the things they didn't buy. So if you bought Pepsi, we know what the price of 7-Up and Coke is. If you bought 7-Up, we know what the price of Pepsi and Coke were at those stores. So we've got these three brands of soda. We've got the prices of those three brands, and we've got the promotional activities of those three brands in terms of the features and displays. So just to try to get acquainted with this whole process, let's take a look. No, 7-Up is the most popular, at least in this sample.
It's actually somewhat surprising. Coke is last.
Yeah.
What?
It is. These are percents. They're not that widely distributed or disparately distributed. Let's see. I'm going to use a pie chart. Again, all of these can be done infinitely better even in Excel, not to mention Tableau. Never underestimate summary statistics. It's where you're going to find problems. It's where you're going to. All right, so we can sum these three. Let's look at. Oh, these are for 2 liter bottles. So it looks like on average Pepsi's a little bit more
16 cents.
than Coke, and then 7-Up. Yeah, those are pretty cheap. 16 cents.
To $2.99. It pays $2.99.
Yeah.
It's kind of crazy.
This could be damaged though, right? You ever go to the checkout and they got the basket with all the damaged stuff? Maybe the label's peeled off, or it's been left out for whatever reason.
Left out.
So that could be it. Let's see how these prices look. Graph.
Are they? Is it so good?
Yeah, they're all pretty close. Remember the middle bar, or the bar in the middle of the interquartile range? Remember that in our box plot? This is the 25th percentile. That is the 75th percentile. And the line in the middle is the 50th percentile or the median price. So it looks like, they're not all that, the distribution of prices isn't all that great, but it looks like, again, Pepsi's the most, now it's Coke, and 7-Up looks like at least the median prices are relatively cheap. But they all look pretty closely priced. All right, so essentially, and I think I can do this in it. Essentially, this is how the data comes from Nielsen or IRI. It comes in this, in this format where we get an ID. We got dummies for each of these. Here's a dummy for Pepsi, for 7-Up, for Coke. And when the dummy equals 1, it means that's what they bought. So we can see the first few bought Coke, then we got some Pepsis, and then we don't get a 7-Up for a while, at least not in these first few observations. Oh, there we go. Here's some 7-Ups, and so on. This, again, this isn't set up for analytics. This is set up for, this is just the way the data comes from IRI. So we need to construct a variable that is going to allow us to use our multinomial logit process. We're going to call it, I'm going to call it choice. We can call it purchase choice. And remember, the order doesn't matter. So in this particular case, and I don't know why I chose this, but I'm going to generate choice equals 1 if the dummy for Pepsi is if you chose Pepsi. It's 2 if you chose 7-Up. It's 3 if you chose Coke. Again, this is ordinal. The order doesn't matter. I'm sorry, it's nominal. The order doesn't matter. So we could have changed these any other way, and our result would be exactly the same. That's a big difference between the term I used earlier, ordinal. So nominal means order doesn't matter. Ordinal means the order does matter. So if we're looking at survey results, right? Pepsi's sending out a survey, or it's got a panel of people. It's asking them survey questions like, what is your favorite? 1 is Pepsi, 2 is Coke, 3 is 7-Up. There, the order matters. Or do you not agree or not agree with the statement that, blah, blah, blah. 1 is agree, 2 is neutral, 3 is disagree, or some measure where the order of the responses actually matter. Here, it doesn't matter, so that's a big difference between those two kinds of models. We'll get to that now. So we've generated that. We can tab it, and it's just going to be that linear 1, 2, 3. And the count is going to be similar to those, right? 34%, 37%, 27%. So it's, again, the order doesn't matter. Those are the relative frequencies or the percentages. I'm going to label these so that when I tab it, I don't see 1, 2, 3. When I tab it, I want to see what the heck 1 is, what the heck 2 is, and what the heck 3 is. So now I know 1 is Pepsi, 2 is 7-Up, 3 is Coke. And I like value labels. Because I hate having to double check stuff. Here's a simple list. And each row represents a purchase. And again, this is the unique thing about these home panel data sets, is they're set up so that not only do you have the price of the product you purchased, they have the prices of the products you didn't purchase. So let's see. All 3 were the same price for the first person. For the second person, they purchased Coke, and Coke happened to be the cheapest. For the third person, they purchased Coke, and Coke was not the cheapest, it was 89 cents versus 84 cents for 7-Up, and so on. So for the third person, they purchased Coke, and Coke was the cheapest. All three were the same for the fifth. Pepsi was the cheapest for the sixth, and so on. So again, we want to kind of use this kind of binary. Yes, I bought it. No, I didn't buy it. Across the prices, and see if we see a consistent pattern of behavior.
Well, that just exemplifies brand loyalty.
Yeah, so we're not necessarily going to get, like we do with the Heinz and Hunt's, we're not necessarily going to get a full S, let's say. All right, so here's a simple multinomial logit. So our command is mlogit. There are our results. We don't have any independent variables, so we really can't say anything. So in essence, when we run this, this is basically telling us our relative frequencies. Remember, these aren't percentages, these are changes in the log of the relative odds ratios. But we do know this. Multinomial logit throws out or uses the base category with the most observations. So this tells us that Pepsi is less likely than the base. It's negative and it's significant. Well, it's actually not very significant. Pepsi is less likely than the base 7-Up, and Coke is less likely than the base, which is 7-Up. But that difference is statistically significant. So remember, Pepsi and 7-Up were pretty close in the 30 percentages. This isn't all that important. We can use, but it is important to predict for specific outputs. So if we want to predict for the first outcome, I should say, and that first outcome is Pepsi, we have to specify what we're predicting for. So, and again, these are just going to be relative frequencies, 34%. If we don't specify for a specific outcome, for example, if we just leave it blank and type margins, it's going to give us basically at this point, because the model is a simple model, the relative frequency for all three of these. And again, you can see those first two are pretty close, and that third one is Coke, and it was statistically different than the other two. All right, so let's add in these prices. Not simple. So here's our choice based on the relative price, not on the relative prices, but on the prices of Pepsi, 7-Up, and Coke.